So we have 4 speakers, and we'll have our 4th right now, and then we'll have a discussion, and then we'll move on to some other summaries. But first, I wanted to introduce Stephanie Dutkiewicz, who's going to talk about physiological diversity matters, a modeling perspective. Thanks.
Thank you. How does my sound? Good? Up more, or it's okay? Okay, that's like good, not up, right? Maybe that should be up, and that's good. All right. Thank you very much to the conveners. This is an exciting session. And you've heard some great physiological talks. Now you get to hear the modeling aspect, so how we mess up all that interesting physiology. I'd like to start off by acknowledging several people who've, through working with or discussing with, have helped with the work that I'll be showing, as well as the funding opportunities that we've had, particularly NASA and NSF. Thank you very much to those of you in the audience. I'm going to talk about global 3D biogeochemical and ecosystem models. I'm particularly going to be focusing on diversity, so diversity of physiological strategies. So I'm going to go through a very brief history of how we've put different diversity into numerical models. I'm going to then show some examples using my own model of where some different aspects of physiological strategies matter. And then, provided I have time, I've thrown in a bunch of slides that we're hoping to tie up with the other 3 speakers. So we'll see how many of them I get to. I wanted just to start and put us all on the same page is what I mean by a 3D biogeochemical and ecosystem model. It's a model that includes the physics, so things like the temperature, the currents, shown here in white. And then also on top of that, the biogeochemistry, so how the nutrients are moving around. And here this is just shown by nitrate, but the models include things like iron, phosphorus cycle, silica cycle, as well as dissolved and particularly organic matter. And then on top of that, we put an ecosystem. And generally, the ecosystem only goes up as far as the zooplankton, but how we put the phytoplankton and the zooplankton on top of that. And so that's the part that I will focus on, particularly the phytoplankton aspect. But remember that underneath that all is this moving ocean and the biogeochemistry as well. Whoops. So that's, that ecosystem is trying to represent an incredible diversity of phytoplankton. We know that phytoplankton range in 9 orders of magnitude in size, and that there are incredibly different biogeochemical functions that I think we've heard quite a bit about. So how have we tried to incorporate that sort of diversity in these 3-dimensional large-scale models? Well, initially, computational expense being a problem and our knowledge of all that diversity being an issue, phytoplankton, the first models just put one phytoplankton in. So it was one thing that photosynthesized, and it was representing all that diversity. And in fact, could do a remarkably good job. I mean, it got where primary production was supposed to be high and where it was not supposed to be high because it was linked with the biogeochemistry. But it rapidly became obvious that that was too simplistic, and we know that the subtropical gyres are dominated by tiny, small-growing cells, and the higher latitudes by faster-growing diatom-type cells. And so the next generation of models included at least 2 pools of plankton, which were supposed to represent all of that, all the small stuff and all the big stuff. And again, it led to an improvement on how those models captured what was going on. But even then, we knew that we were missing things, particularly things like nitrogen fixes, which were really important to the nitrogen cycle. And so the next generation of models included different pools to include those functional groups. But again, it was one pool that was including all that functionality. And most of the models in the CMIT-5 were of this nature, just 2 phytoplankton. And stop me if I'm wrong, but I think a lot of the CMIP6 probably are more of this feature where they have a few more, but it's still a handful of functional types. There's been additional work that's been done in the last few years on trying to put a little more diversity into the models. So for instance, we know that that incredible range of sizes is really important. And the nice thing about the size is that it seems to be tied, a lot of the parameters, a lot of things like growth rate, uptake rates, nutrient affinity appear to be related quite strongly to size. And check that I get the right one here. This is a representation where V is the volume, and you can actually do a lot of the parameters within the model based just on knowing an A and a B and the volume. So we can say something about growth rates just based on those two parameters. And so using a lot of work that has been done over the years looking at allometric relationships, Ben Ward, for instance, added size to 3D models. Ben also did some work where he, instead of looking at functional types, looked at the level of mixotrophy. So the range of this axis now is going between autotrophs and heterotrophs. And I think he'll talk a lot more about that later on today. So where are we? A lot of models still have just a handful of functional types. That is computationally related. You can't put in hundreds of phytoplankton. And also there is something of a lack of knowledge of how we should be putting in all that extra diversity. But there are some models, and usually the ones that try to look more specifically at ecological questions rather than biogeochemical questions, that have really addressed putting in large numbers, tens to hundreds to thousands of different phytoplankton types. Some of the work that Ward does, where he sets the traits, such as the size, and then a couple of models that have done a random assignment of traits. And we heard from Victoria yesterday about a model such as that. So I want to just show a few of the things that are starting to be put in the models as to why they may be important. In particular, if you're asking a particular question, you might want to include additional diversity. So I'm going to go through size, trophic strategy, and symbiosis, and hopefully I will get through all of them. Let's see where I am already. So first thing, putting some size into how we look at functional groups. So there is a range in size of diatoms, not just one big pool. So what we've done in a recent version of our model is to do just that, is to include a range of sizes within the different functional groups. And this is getting to, like wherever Jeff is, a complaint that models were stuck on no diversity within functional groups. So we're trying by doing this allometric approach. And again, the nice thing about putting the size part in is that you can use some allometric relationships that we at least empirically and sometimes theoretically understand. For instance, this is a diagram of the maximum growth rate against cell volume. And all of these dots in here are from laboratory experiments looking at the maximum growth rate and studies that have also then looked at the cell volume. And you can see a very definite decrease with size in the maximum growth rate. But these dots here are color-coded, and that one's supposed to say coccolithophores, but you can't read. So the dark blue coccolithophores, the red diatoms, the purple here, dinoflagellates. These ones down here are nitrogen-fixing diazotrophs, and these are the picoplankton. And I could spend the rest of my time, and plus some more, going through some reasons why there may be these differences in slopes between the picos and the larger eukaryotes, and why they may be different A's, different intercepts. But we'll take that as a given because we empirically see it, and we'll move on to the model where now the large symbols are my model organisms. So empirically based, I'm going to give different functional types, slightly different intercepts here, and different slopes in the case of the pico eukaryotes. And I get a model like this. So each of those is a model phytoplankton type. On this axis is the functional groups, and this axis is the size. And for instance, here we're getting a range of diatoms going from about 3 microns up to about just over 200 microns. Phytoplankton, with some of the larger size of classes, only exist because they are grazed by a range of zooplankton. So I have different size classes of zooplankton, and I have a different axis here for their sizes. And so we can get this incredible diversity, but without adding too many parameters to the model, which is exciting. But you may say, so what? Let's just think about if you were really interested in the size distribution in the ocean. Well, this is the size distribution of the phytoplankton in a model that has just 2 phytoplankton, so a pico-eukaryote and a diatom, and 1 zooplankton. And you can see this huge, there's large ones and there's small ones, and there's not much in between. But when you have this range of different sizes, you can get a much more realistic distribution with some slightly larger phytoplankton in these subtropical gyres. And again, all right, so maybe that's kind of nice, but again, is it important? Well, let's take this particular model and send it into the future and ask what's going to happen. So we are going to a business as usual scenario, so like an RCP 8.5, much warmer world. There's changes to the stratification, changes to the circulation, and therefore a lot lower nutrient supply. And what we find is that there is a significant decrease in the size of the cells. So we can see it's in sort of about 2 microns overall, but with some regions with dramatic changes of about 10 microns. Now, most models have suggested a decrease in size between models, but it's between 1 large one and 1 small one. And so these sort of actual numbers could be really important if you're thinking on trophic levels. It could also be really important if you're thinking about changes in export, if we assume that larger phytoplankton are responsible for more export. This is a graph of how the community changes. It's a complicated equation there, but basically if it's 0, it means the community is the same. And if it's 1, it means the community is completely different. And you can see that it changes over the course of the century. And I've differentiated in 2 ways. One is if we just look at how the functionality changes. So does a diatom disappear and a coccolithophore take over? Or some diatoms disappear and some coccolithophores take over. The other one is the size differentiated. Does a larger thing take over, a smaller thing take over from a larger thing? And you can see that in terms of size, it's actually a much bigger change than it is in terms of function. If I then take that 2 phytoplankton model with this 1 zooplankton and I look at the same thing, it has to be functionally differentiated because that's what it's based on. And you can see that there is a significantly bigger change expected than, especially in terms of function, than in this model here. And what's happening is that in the 2 phytoplankton case, if there's a change, it's a change between a big diatom and a small phytoplankton and a small picophytoplankton. But in the more nuanced model, it's a change between a big diatom and a small diatom before there's a change to a smaller phytoplankton. And so it's making a much more nuanced response, which could potentially suggest that we're overestimating the changes that will happen in the current versions of climate change models. So I want to go through a couple more examples, so I better move on. Oh, I just wanted to put in, after yesterday, we don't have evolution in this model, so let's put question marks on some of those. All right, so the second one that I want to talk about is trophic strategy. So there's not just autotrophs and heterotrophs in the ocean. I think everyone knows that and it's not in this group, but it's been something that's been fairly difficult to put in models. And this is some observations from paper by Andrew Barton, looking at CPR data, so continuous plankton recorders, so it's mostly the larger size eukaryotes that they're looking at. They've been divided into different sections in the North Atlantic. And this is sort of averaged along these C sections here. This is the mean abundance of diatoms and then mixotrophic dinoflagellates. So after you have the spring bloom, you have the later time having mixotrophic dinoflagellates. So if we put a mixotroph into our model, so mixotroph in the model is represented as something that is not particularly good at photosynthesis and not particularly good at grazing, so it's not going to become a superbug, but it can do both. And so it can supplement what it can't get from photosynthesis, from grazing, and vice versa. And here's two simulations, one without mixotrophy, one with mixotrophy. And you can see a diatom bloom, and then it's followed by the smaller phytoplankton, the picos and the coccolithophores. But when we put mixotrophy in, we get what was observed from the CPR data as a later bloom of mixotrophs at the expense of these smaller phytoplankton. And if we look at the mean diameter, which is on this axis here, we go from much smaller diameters to much larger diameters. And this is similar to some of the work that Ben Ward found, and we'll hopefully talk about later on today. But what it also does is change the timing of that maximum, of where the maximum size classes are. And actually, I think I'm a little bit behind time, so I'm going to skip through that. So to be able to capture some of the larger size classes later on in the spring, later on in the summer, the largest species in the summer, mixotrophy is fairly important to include. So the third example I want to show is symbiosis. And again, here's Jeff and Morrison, the audience. This is in response to the fact that most of the interactions we have put into models at this point have been negative, as in one thing eats another. Well, here we've tried to put in something helping one another, helping each other. The example is started as looking at some observations for Station Aloha. This is a particulate biogenic silica, and you can see this peak in about July, suggesting that there's some diatoms there. This is the middle of the subtropical gyre, so kind of interesting. And it's followed by a particularly large peak in export production, in carbon flux, so export production. So when you go out and you have a look at what sort of diatoms are there in this bloom here, these are this is a photograph from Chris Follett, and it's showing up sort of okay. So this is a picture of 3 different diatoms, tracing them out here. This is 550 microns, so these are actually quite large diatoms. So in the middle of the subtropical gyre, these large diatoms. But what is important about them is they're all associated with a nitrogen fixer. So these are what we've got termed diatom diazotroph assemblages, DDAs. So if I look in my model, so I've shown you this graph before, and I zoom in on the diatoms, and the red dot is now sort of Station Aloha. We get a few tiny diatoms in that region, but we don't get any large ones. So obviously we're not capturing something that's important for getting large diatoms. And, obvious wing is what we need, some symbiosis there. And so Chris Follett has a very nice paper trying to explain diatom diazotroph assemblages in the North Pacific. And as part of the paper, he wanted to show a sort of global representation. So he persuaded me to try to put a DDA in the model. So how did we do that? First of all, we had a look at measured growth rates of here is diatoms. So that's the range of diatom growth rates. This is a range of trichodesmium growth rates, crocospherides growth rates, and diatom diazotroph assemblages. So this vast range of diatom growth rates is somewhat based on the fact that we have a range of sizes depending on, a range of growth rates depending on the size. So large growth rates for smaller sizes and slower growth rates for larger sizes. This is sort of the size of a unicellular diazotroph and its growth rate. So if you're having a symbiosis, you kind of want to be growing at approximately the same rate. So we just defined a DDA as a small diazotroph living with a large diatom, and so that their growth rates were somewhat similar. And if we put that in the model, we get diatoms growing in the subtropical gyre. So this is in a region around Aloha. The black line is a simulation without putting the DDA in. So a few diatoms, but they're mostly the really small ones. When we put the DDAs in, we get this huge spike in the summer of diatoms. And then if we look at the export from this model, again, without DDAs and with DDAs. So it's not quite as dramatic as actually seen at Aloha, and therefore we have to go back to the drawing board and think more about it. But there is definitely an impact on the export because of these DDAs. And so if you happen to have a problem where you were really wanting to consider export around Aloha, if you didn't put a symbiotic relationship such as a DDA in there, you wouldn't be able to capture the export. I just wanted to note that if you want to see sort of trying to include non-negative interactions, at least in a 0D model, there's a poster by B.B. Kale showing how we might begin to put it into more such interactions within not so much symbioses, but the mooching aspects that Jeff talked about yesterday into numerical models. So the next generation of ecosystems models do need to include some diversity of physiological strategies. Whether it's sensible to do that in all models is definitely a question, but certainly depending on the question you're asking, including some of that physiological differences and different strategies will really be important. And I am out of time. By how much? Okay, so I just wanted to show I shall show one slide. Is how we do stoichiometry within the models. And Adam has spoken about this fairly well, so I don't just wanted to remind everyone before we go into the discussion that an awful lot of the models use what we call monokinetics. So growth is just determined by what's coming into the cell from outside. Some models have moved on to using cell quotas, just having these big pools of of different nutrients that come into the cell, and then the growth is decided by that. And then more complex models, and Richard showed an example where you actually look at what's happening in the cell to be able to decide what those cell quotas should be. And just going to some of the work that Erin showed, we have ideas of how phytoplankton might grow as a function of nutrients, or as a function of light, as a function of temperature, but we don't know how they grow with the combination of them. In the model, we usually use a minimum for the nutrients, but we use just a multiplication for the other nutrients. And it gives something like this, which is, if you just multiply a nutrient curve with a temperature curve, you get a plane like this. Don't worry about the lines. The plane has some interesting features. So you can see, for instance, the drop-off here. How realistic are these? Do we want to do thousands and thousands of experiments, as Phil discussed, to try and fill in what this plane should be? So I'll leave just some questions that hopefully will suggest some thoughts for discussion, and when we get to sit here and thank you.
It's awfully dark out there. We'll take one question before we have all our speakers come up and field additional questions. One question perhaps specific for Stephanie. I see one in the corner.
Hey, Steph. So given that there's really no measured seasonal cycle in nitrogen fixation at Station Loha, I'm curious what in your model is driving your pulse of DDAs in that 1 month?
I haven't actually looked at what in the model. There may be a different seasonal cycle in nitrogen fixating because there are also unicellular types, so it's probably a longer seasonal. In this model, the reason why the DDAs pop up there is a light and a nutrient, the environment. Chris's paper, Chris Follett's paper, really discusses that combination that is just optimal for the DDAs just in those months. But it's the temperature and the light the nutrients and the light that is important for that combination.
So I'd like to thank Stephanie.